Section 10.3 of the conic section chapter is our first look at ellipses. So this is our first conic section. Now, we're going to cover most of the kudos in this first part of our video, but after that, for part 2, we're going to come back to the focus and to completing the square. So this first part is going to really give us a general idea of what's the equation look like, what do the graphs look like, and what's some of the information that we can find from either a graph or an equation. Now, conic sections in general are sections of cones. Conic sections, right? Now, if we take a cone and we take a plane and slice that cone horizontally, we're going to get a perfect circle. Now, if we tilt that plane at a little bit of a diagonal, we can't go too far, but if it's slicing through the whole cone, we'll get what we call an ellipse. So it looks kind of like an oval, is what you might call it, but we're going to call it an ellipse. So before we move on to the ellipses, let's first recall what we know about a circle, because this is something that we've talked about before. So you can see example 1 here, we've got x minus 1 squared plus y plus 2 squared is equal to 16. So just a reminder of our general form, we've got x minus h quantity squared plus y minus k quantity squared is equal to r squared. So where we have h comma k being our center, which in this case, that would be 1, negative 2. We also know that r is our radius. So if we take the square root of 16, we're going to get r equal to 4. So graphing this, we're going to start at our center, which is 1, negative 2. And in any direction, horizontally or vertically, we're going to count 4 for our radius. So we go over 4, we go up 4, go to the left 4, go down 4. And we get a nice circle. Do the best you can to connect those with a nice circle. Pretty straightforward, right? Now you can see if we manipulate our equation a little bit, we should be able to come up with an ellipse. So that's what we're going to look at for these notes. All right, we've got 2 different equations. We have a horizontal major axis. We also have a vertical major axis. So you can see on the left here, our circle is kind of stretched out the long way, and on the right, it's stretched out vertically, the tall way. Okay, and we'll talk about sort of what determines that. But for now, let's start by labeling some things. So right in the middle is what we call our center, and we're going to call that HK. So go ahead and label that on both of your ellipses. Okay, that's our center. And like I said, horizontal major axis, we're going to label our major axis. So it's that horizontal one. That means that this vertical one would be our minor axis. Okay. And then kind of likewise on the other, our horizontal axis here is now our minor axis. It's smaller. And our vertical is our major axis. Okay, now you see we also have these quantities A and B that are listed underneath our variables. So A and B represent lengths along our axes, where A is the length from the center to either endpoint of the major axis. And we'll label that on both figures. So A would be the vertical distance from the center to the endpoints of the major axis on the right. And B is going to be the distance from the center to the edge of the ellipse along the minor axis. So we can label those. Okay, that's going to create the length of our major axis is 2a in both cases, right? A plus a. And the length of our minor axis is going to be 2b. And that's going to be helpful when we're trying to work from one form from a graph to an equation or vice versa. Okay? Alright, that should be everything that we need for now. Now let's notice, in both pictures, notice that A is always greater than B, and both of them are going to have to be greater than 0, and that's just so that we actually have a shape. If one of them was 0, it would just be a straight line. It doesn't make any sense, right? It wouldn't be an ellipse. The second thing I want you to notice, okay, is that A goes with our major axis. So if A is with X, it's horizontally oriented. And if A goes with Y, so you can see in our second equation on the right, A is underneath the Y minus K term. So if A is with Y, then it's vertically oriented. So that makes sense. Okay, so keeping that in mind, we're going to get some more formal definitions about the different information here. To start off, we've got our vertex and our vertices. So the vertex, each vertex is an endpoint. These are the endpoints of the major axis. Okay, so there's two vertices in every ellipse. These vertices are equidistant from the center, and they happen to be a distance of A away from the center. And we just labeled that. Okay, our major axis is going to be what we call a chord. So a chord that connects, so a chord connecting the two vertices passing through the center. So a chord runs from one edge of the ellipse to the other edge. This one goes straight from vertice to vertice going through the center, and it's going to have a length of 2a, and we labeled that also on the diagram. Now the minor axis, kind of similar to the major axis, this is going to be a chord perpendicular to the major axis, and it also passes through the center. And this one has a length of 2b. Has a length of 2b. Okay. Finally, our center, as we've already found this for a circle, our center we call HK, and it's the midpoint of both major and minor axes. Okay, so it's kind of the middle of all this action. All right, so I think it's going to make more sense if we actually see some numbers involved here. So looking at example 2, we've got x squared over 9 plus y squared over 4 equal to 1. So we want to start by identifying everything we know, and then we're going to end up graphing it. Okay, so a couple different ways of looking at this. Let's find a and b first. So if we know a squared is 9, then we know a is 3. And if we know b squared is 4, then we know b is 2. Now I chose a and b this way because I knew that 9 was bigger than 4, so 9 has to go with my a term. Okay, so one way that you could rewrite this is by x squared over 3 squared plus y squared over 2 squared equals 1. Notice we always have our ellipse equation equal to 1. Okay, if we do it that way, now you can clearly see what's a and b. Whatever's with x is going to run horizontally. Whatever's with y is going to run vertically. Our center HK is 0, 0, because there's no subtraction or addition going on with the x and y terms. And our vertices are the endpoint of our major axis. So let's actually start to get our graph going, and then we'll see where our vertices end up. Okay? So our center, 0, 0. Let's start by plotting that to get us an idea of where to count from. We determined that because A is with x, it's going to be horizontally oriented. So we're going to go 3 to the right and label that point 3, 0. We're also going to go 3 to the left and label that point negative 3, 0. Our minor axis, B, is a distance of 2, so we're going to go up 2, and we're going to go down 2 from our center, and that will give us the shape of our ellipse. Okay. So we'll label the rest of those 0, 2, and 0, negative 2. So noticing on our graph that our vertices are plus or minus 3 and 0. And really what you do to find these is you're taking your h value and you're adding and subtracting your a value. And then you put your k value as your y value. So that's sort of the formula we could use. Well, h is 0, a is 3, k is 0, and that would give us our vertices. Now, if our vertices were vertically oriented, we'd have plus or minus a with the k term instead of the h term. Okay, let's go ahead and try another example. This one, you can see right away that x plus 2 squared and the y minus 1 squared mean that we have a shift. So we could identify our center. It's going to be negative 2, 1. Okay, then let's also take some time and rewrite our a values and b values. So here, 36 is larger than 25 fourths. So it turns out that if I want to rewrite these as perfect squares, I'm going to get x plus 2 squared over the quantity 5 halves squared. Then I'm adding y minus 1 squared over the quantity 6 squared. So you can see a is 6, b is 5 halves, so 2.5. A is always bigger than b. So here, this time a goes with my y terms. It's going to be vertically oriented. And my equation is still equal to 1. I can't get rid of that equal to 1 part. All right. The length of the major and minor axes. Let's go ahead and find those. So the major axis would be 2 times a, which is 2 times 6. So we get 12. And the minor axis has a length of 2b, which is 2 times 5 halves, which is 5. Okay, those should show up on our graph. We found the center. Last thing we're going to do is find our vertices. So this time, our vertices are going to be above and below our center point. So my h value is the x-coordinate of my center and my vertices. So I'm still going to be at negative 2. But what I'm doing is I'm taking my k value, which is 1, and I'm adding and subtracting my a value, which is 6. So that's going to give me negative 2, 7, and negative 2, negative 5. I'm going to also box off our center point, because when we start graphing it, we want to make sure that these things match up. So starting at our center, we go to negative 2, 1. Major axis is with y, so I'm going to go up 6, 1, 2, 3, 4, 5, 6. I'm also going to go down 6, 1, 2, 3, 4, 5, 6. Those would be my 2 vertices. From the center point, I want to count my b value to the left and right, which is 2.5. Okay, and I can now draw my ellipse. You can see it's elongated vertically. And let's make sure that our vertices match up. So -2, if you count the squares, that goes to 7. And -2, -5. So our original algebraic math worked out. It matches our graph. All right, we've got one more example. This time we're not given the equation. We have to come up with it. So in example 4, we're given vertices 1, 7, and 1, -3. We're also given a minor axis of length 8. So here we want to produce a graph and determine what the equation would look like. So if the minor axis is 2 times b, and that's equal to 8, then we can see that b is equal to 4. So that's going to play a part in our equation. I'm going to start gathering our equation on the right here above our graph. So we know that we have 2 fractions and they're equal to 1. I think next it's going to probably be easiest to find our center point. So our center is the midpoint of our major axis. It's also the midpoint between our vertices. So you can see the x value is going to be 1, and the average of 7 and -3. So 7 plus -3 is going to give us 4 over 2. It's going to give us 2. Okay, so the y value of the center will be 2. The x value is still going to be 1. Let's go ahead and put that into our equation. So we get x minus 1 quantity squared, and we're going to get y minus 2 quantity squared. Because these points, let's graph our vertices. They're at 1, 7, and 1, -3. We just found the center as well, which is at 1, 2. So you can see this is a vertically oriented ellipse, which means that our minor axis is horizontal. So it goes with x. So I'm going to put the b value is 4. That goes with x. We have to square it, so we're going to get 16. Okay? And we can go ahead and plot that. So from our center, we can go over 4 in both directions. And we can make our graph. Looks almost like a circle, but you can tell the major axis, the vertical, is a little bit longer. It's a little bit stretched out. All right, last thing we need to find is our a value. And our major axis from 7 all the way down to -3. If I want to know the distance, I can take the absolute value of the difference between them. So -3 minus 7, absolute value of -10 is 10. Or I could look at my graph. You can see from 7 down to -3 is a distance of 10. That's equal to twice a. So a is equal to 5. I'm going to square that and put it underneath the y term. I get 25. All right, I want to flip back to the very first example we did dealing with a circle, and I want to talk about one kind of connection between ellipses and circles. So you can see with our circle equation, let's take that equation and we're going to divide it through by 16. So I get x minus 1 quantity squared over 16 plus y plus 2 quantity squared over 16 equal to 1. Now it looks like it's in the form for an ellipse, except that we have a equal to b, which happens to be r. So if it's a circle, that's always going to be true. Your major and minor axes are exactly the same. They're just twice the radius, which happens to be the diameter. Okay. All right, your job is to finish that last example at the very bottom of the notes.